Okay, so you're given some vector and a function. So notice how my function right now is written implicitly, meaning that it's just one function normally, like an equation. And we're given some point A. Well then, let's find what df is. So if you're given this function, we know how to find the derivative, right? The Jacobian matrix. We do the partial of f with respect to x and the partial of f with respect to y. So what does that give us? Well, that would give us ey minus y sine xy, and then xey minus x sine xy. This is our 1/2 matrix. And specifically, we're given the point A. So why don't we evaluate it at A, right? A is 2, 0, 2, 0. That gives us a 1/2 matrix with inputs 1, 2. So if a question asks, find the output rate of change f dot for the input rate of change x dot at A, if x dot is x. So right now they're telling us your input function, input vector is this 3, -4. And we're asked to find the output rate of change. And we know the derivative, so we just plug everything in. F dot equals our derivative, 1, 2. The vector we're given is 3, -4. So this answer is -5. Now, what if they say find the output rate of change for the input rate of change x at A if x is the unit direction? So same question as part A, but now it says unit direction. What does unit mean? It means that we need our vector to have length 1. So what do we normally do to normalize something? We divide by the length. So right now we have our matrix, but this vector, what is the length of 3, 4? Length of 3, 4 is square root of 3 squared plus -4 squared, which is 5. So for each of the terms, we divide by 5, -3/5 and -4/5. We multiply that and we get -1. But now what if they say part 3, find the directional derivative along u at A. So now the only difference is that we've changed languages, kind of. So what was our derivative matrix? It was this up here. But what did I say about the gradient? I said that it's written vertically. So this is the partial with respect to x, the partial with respect to y. And we get the same thing, but written vertically like this, 1, 2. So now we use our formula. So the formula says that the directional derivative, so d sub u of f, equals the gradient, which now we know is 1, 2, like this way. And then u, as I said, should be a unit vector. We found what u is here. It's times 3/5. Okay, wait, let me write it this way actually. Okay, it doesn't matter. Like this, ln 3/5 -4/5. And now that's just a dot product, right? Dot product gives you a single scalar. So you get the same answer of -1. And yes.
Did you go over part B?
Yes. So part B says find the output rate of change for the input rate of change where x dot is the unit direction of v. So v itself, v right now is 3, -4. But the length of v is not 1 right now. We need to normalize it. So in order to normalize it, well, the normal vector u should be v over its length. So we have 3, -4 over its length. And when you divide by something, make sure you divide each term. So you have 3/5 and -4/5.
So is the gradient calculated the same way that you would calculate?
Yes. Yep.
If our answers for B and C are the same, what's the difference to the question?
There's no difference, just different languages.
Okay.
So yeah, that's the point of like, now that we've changed languages, if we wanted to think about it in terms of linear algebra, which we've done the previous weeks, basically the same thing, but we want that vector, that unit input vector to be units, meaning length 1. Okay. Oh, any other questions? Okay, so let's move on to the angle. So here we have definitions. Let theta be the angle between you and the gradient of f. So it's the angle between you and your gradient. Then we notice that this is our formula here. du of f can also be written this way, where you have the length of the gradient times cosine theta. Why is that? Because up here in the yellow, that's how we just define the gradient, right? But we know that the dot product between any two vectors, we know that the dot product u dot v is always the length of u, length of v, cosine theta. So if we just let u be gradient f and v be u, then we get gradient f length times length of u times cosine of this angle. But remember that u is always unit length. So this is 1. This is 1. So you're just left with the length of gradient times cosine theta. Oh, yes.
And then if that equals 1, when it's orthogonal, you know it's on a level, and you know it's the maximal increase off the level set or something.
Yes. So I'm getting into that next. So let me do a question here. Oh, wait. Okay. So here's the definition. Say, if you have the same direction as your gradient, then that means f is increasing most rapidly when u is going in the same direction as f. So you can picture it like you have a u here, and then your gradient is also going this way. Then the angle between u and gradient of that angle is 0. So plug in 0 to our function here. Cosine of 0 is 1. So you'd just be left with gradient of f. And so that's why when the angle is 0, your directional derivative will just be the length of your gradient of f. So that's some intuition. Now, if you have the opposite direction with your gradient, so think that this is u, and this is gradient f, that's 180 degrees. Cosine of 180 degrees is -1. So you get a negative out here. So that's why your u should be negative of the normalized gradient. Then if u is orthogonal to the gradient, then f does not change, meaning that if you have u here, oh yeah, u gradient of f, this angle is 90 degrees, and oh, I just erased it, but cosine of 90 degrees is 0, so that whole term would go to 0. So we want the directional derivative equal to 0. Okay, so in this example here, from recitation question 67, we have an ant traversing some anthill, and the temperature is given by T. So notice again that our equation is given as an implicit equation, meaning there's one formula, one output. So our function right now is T of this. Oh, okay. Then we want to know, well, the first question says, at some point, in what unit vector direction must the ant move so that the temperature increases most rapidly? So that should be this definition here, right? We're trying to find the u so that our f increases most rapidly. So we should be using this definition. And in order to use this definition, what do we need? We need the gradient, first of all. So let's find the gradient. So let me do the gradient on my iPad. So this is our function. The gradient, this first value should be the partial of t with respect to x, then the partial of t with respect to y, and the partial of t with respect to z. And if you evaluate it at the specific point they gave us, which is square root pi 0, then we get that the gradient of t is this vector here. So gradient of t equals negative square root pi, negative square root pi, square root pi here. Okay, so then back to the question, when does it, any questions? Okay, so then now we're trying to solve this, right? So we're trying to find u. So u should be, well, it says to take the gradient, which was negative square root pi, negative square root pi, square root pi. But we want to divide it by the length. So what is the length of this? It's square root of negative square root pi squared, negative square root pi squared, plus square root pi squared. So that's pi, which is square root of 3 pi. So we have 1 over square root 3 pi times this vector. And you can even simplify it more because you see that we have like square root pi over square root 3 pi. If you put everything under the same radical, you get pi over 3 pi or 1/3. Yeah. So you could even write this as negative 1/3, negative 1/3. Any questions on how I did that? Yes.
Wait, so I'm just kind of like confused. Like, so what's the answer to this one?
So the answer to part A, so it's asking in what unit vector direction. So the unit vector direction is this vector. And it's a unit vector because the length of this is 1. And you can check. The length of this vector is 1, 9 plus 1, 9 squared. Oh, sorry. 1 over square root of square. Length of it is 1/3 plus 1/3, which is 1. So the answer to part A is this vector. Yeah.
You're finding something that you multiply by the multiple gradient to get with.
So we're given some space. We're given the gradient f. And we want to find which way do we go so that f will increase most rapidly. So if we're going this direction, then like you're kind of like moving this way and you're being influenced by this direction. Like, so you're kind of like overall moving this way. We don't want that. We want this direction to be the same as our gradient. So we're finding what is this direction, u. And specifically, we just want it to have unit length. So that's why we need to divide by the length. So we're finding what is this u. It's f, and then normalize it. Let's do the other direction. You see if that helps. So we want to find in what unit vector direction must the bug move so that the temperature decreases most rapidly. So now we have like okay, this is our gradient f, but we don't want the temperature. Oh, I should be calling this t. Sorry, gradient of t. We don't want our temperature to keep increasing. We want it to go the opposite way. So we want to find a u that's like this. We want to find this u. And specifically, we want the length of u to also be 1. So what do? Well, we follow our formula. It says negative of the gradient of f over the length of gradient of f. Well, we just found what gradient of f over the length of gradient f is. We just found that that's this. So we can literally just take the negative of it. Negative. Because now it's just going in the exact opposite direction. We know it's unit length. Okay, then part C says at what point, at the same point the bug moves in the direction of this vector v, what is the rate of change of the temperature in this direction? So it says, what is the rate of change of temperature? Temperature right now is our output, right? We're putting in some x, y, z, we're getting out t. So what equation should I be using here? Do you guys think? Yes.
A times x equals b.
Yes, essentially, a times x equals b. But more specifically, because we're in vector analysis right now, we should be finding du f. For our case, we want du of, because I call it temperature, so T equals the gradient of T times this vector that we're given. What is the gradient of T? Well, we found that gradient of T is this vector here. The square root negative pi, negative square root pi, square root pi. The vector they're giving us is 1, 0, 1, 1, 0, negative 1. And then you multiply that, it's a dot product, so you should get a single number. And it's negative 2 square root. Then part D says, at the same point, in what unit vector direction must the bug immediately walk so that the temperature remains constant? So temperature remaining constant means that we want our output F to not change. F does not change, so we should be following this formula. So, if we follow this formula, what does that give us? So we want duf to equal 0. What is duf? Duf is du of t, let's call it, is the gradient of t times some vector. The gradient of t, we know it's negative square root pi, negative square root pi, square root pi. We want to find the vector so that this directional derivative is 0. So some vector a, b, c. We don't know what it's called yet. And what is this dot product? It gives you a number. Right? It gives you negative square root pi a minus square root pi b plus square root pi c. And we want to set that equal to 0. So the answer to this question is that any vector satisfying this equation equals 0 will give you a vector that such that the temperature remains constant. Any questions? Yes.
You plug in a number and that be your answer.
Yes. So for example, if you wanted to try, like you wanted to test, like 1, 1, 2, 1, negative pi plus 2, that gives you 0. That works, and it will give you the correct, it will work out. And I tested it there for you. You get 0. Okay, any other questions on this example? Yeah. The gradient isn't a level set. The gradient is like a vector. Oh, yeah, yes. Okay, so let's move on to level sets. Okay, so took a bit long, so I'm gonna keep going on my iPad now. So a level set is a subset F inverse C. This is just the definition. But that definition is kind of weird, so let me do examples. But first, the level set of F of X, Y. So here you have two inputs. This is going to be a curve in 2D called a level curve. Now, if you have three inputs, the level set of that will be a surface called the level surface. So for example, if you had this function, f of xy equals 100 minus x squared minus y squared, then the level curve of f for constant c is all xy such that your equation equals c. So basically, you take your function, set it equal to c. C represents some number. And so what is this equation? Well, if you add x squared plus y squared on both sides and subtract by c, c is a constant, right? So this equation is a circle because you have x squared plus y squared equals radius squared. What if you have something with three inputs? So f of xyz equals this. Then I said that the level set of a function with three inputs should be a level surface. So you know that you should be getting something in 3D. And so if we set this equal to some number c again, we see that the level surface is going to be a sphere with radius c. Okay, but caution, so we saw a 2D example, curve, and a 3D example, surface. You need to make sure that you pay attention to your domain. Like how many variables are in your input is very important. Why is that? Because if you have this function, f of x squared plus y squared, what is the graph? What does the graph of this look like? Well, it's a hyperboloid. It looks like this. You can graph it on GeoGebra. This is your graph of x squared plus y squared. Now, what do you do to find the level set or level curve, level surface? Imagine cutting through this hyperbola, like cutting slices. Each slice is going to be a circle, a 2D circle, right? Just imagine cutting slices through it. And you can imagine you have this 3D shape projected all down. What does it look like? You end up getting like these circles in 2D because you can picture this small circle part that gives you this when you project it down. The larger circle would give you the second circle when you project it down, and so on and so forth. So this graph has a level curve that is a circle in 2D. Yes. Yeah. Which question? 2? Okay. Okay, so if the level set is going to be a circle, so first of all, how do you even find a level set, right? You're going to take whatever your function is. Let's pretend it's this, x plus y squared. And you set it equal to some number c. That's your level set. What is this graph of? Well, x squared plus 2xy plus y squared equals c. Well, this is some shape. I don't know what it is, but it's definitely not a circle, right? A circle should be x squared plus y squared equals c squared. So we know that this first choice is not our answer. This is not a circle. There's an extra like 2xy here. Let's try this one. No, let's try this one next, I guess. You take your function, set it equal to c. But you can notice again that this is not going to be an equation of your circle because your circle should have the same coefficients out here. So like this would end up being, if you divide everything by 6, this is like a hyperboloid or some paraboloid, some other shape, not a circle. So you can keep testing the other ones and see which one gives you a circle. Which one? Oh, here. Yeah. Okay, because you have a circle. X plus Y. You have a this is a sphere. Wait, a circle. X squared. You have this is the equation of a 2D circle. But when you wait, does this say select all that apply? Oh. Let me see. It might be. Let me check. Yeah. So if you take slices, you get a circle. So it does work.
If you have like a 2D circle, like how would you get it more?
Because you just have a 2D circle and you set it equal to C. So if we set this equation equal to C, you get x squared plus y squared plus c squared. So the level set is just itself. Like there's no other thing to take. You're just taking slices of some 2D circle, and so you get a circle back. Yes.
All right, so then the level set of a 2D circle would end up being the same as the level set of a sphere circle.
Yes, in a sense, but for a sphere, you would have a bunch of different level sets. Because a sphere, you can kind of project, like this top part would give you, projecting down would give you a tiny circle, and then the larger, like the radius part of your sphere would give you this. So the sphere would give you this like level sets, but for the 2D, you just get like single circle.
Does that work at the origin? Because like I feel like at the origin you have point, or where is it?
I think we mainly think of level sets as like the whole.
It's like it's asking.
Centered, it's just saying equal to circles in the plane centered at the origin. So it just has to be centered at the origin, meaning like you don't want something that's going to be like this.
Okay.
Yeah.
It's still this like why you said that when you see.
Oh, sorry.
That would still be a circle.
Yeah, because it's a circle with radius square root c. Yes.
So when you vary C, you're changing the radius
Yeah.
of the circle.
Mhm.
So then what would the level set of that look like?
So the C, let me keep doing an example. So okay, maybe never mind, I don't have it. Okay, let's just keep doing this one then. So if you have a sphere, let's keep doing this one. So so the C is you have, so here I specified C equals 1, but if you just had C equals any C, you have x squared plus y squared equals C is your level set. So if you set C equal to 1, then you get, what do you get? You get x squared plus y squared equals 1. So that's a circle centered at 0 with radius 1. So that's C equals 1. That's your first, that's one level set. If you set C equals to 4, that's a circle centered at 0 with radius 4. So that would be this level set work? If you set x squared plus y squared equals 16, that's a circle, sorry, 2. That's a circle with radius 4. So that would give you this circle. And so all of them can keep gathering. Yeah. Mm-hmm. Yes.
Okay. Also, sorry. So like the level sets that have spheres as level set, so the shape itself would be like a bunch of spheres like nested within each other.
Repeat that.
So for like a shape that has spheres as level sets, like what would that look like?
Then you would need a 4D shape, which we can't picture.
So for that quiz problem, like basically you're just trying to like find the ones where you can set it into the form x squared plus y squared equals some number.
Mhm.
Okay.
Yes. Yeah. Oh, and even in this example, I guess the numbers are kind of tiny, but you see that here I wrote a 1. So at this 1 point, this level set, if you slice it through, that gives you this circle, this purple circle here, this small purple circle. Similar to this example. Okay. So before we continue, I just sent everyone an email. And you can also, let's see, where did I put it? Okay, everyone head to this tiny URL real quick and just please fill out that form while I write out our next question, okay? And I'll give you like about 5-ish minutes. And as if you finish early, you can start thinking about question 1 on the board. Okay, so if you haven't finished the form, you can keep submitting it when you finish, but let's just get started. Okay. So here is questions for how to find the parametric equation for tangent space. So in general, you have this equation. This is always the equation you follow. This is kind of like how from like week 1, I think. How did you find an equation of like a line? You did like, or the equation in my notes was that you would do r equals r naught plus tv. So this was from week 1. Now we're using this equation. So it's similar, right? Except now you have like partial derivatives, etc. So first question says, find a parametric equation for the tangent line at a point to some curve. So you have a curve. You want to find the parametric equation for its tangent like line. First step is you want to so in this question, okay. In this question, we're given something that looks like a matrix. So back to the very beginning of class, what did I say about can you use Jacobian or gradient? Can you find gradient of r? Question mark? Right? Because how do you find the gradient of r? You have 3 outputs. So now you know we don't want gradient of r. Well, we need some sort of like derivative, right? Because we're finding the line for a tangent line. We need some sort of derivative. So our only alternative is we need to find the Jacobian or the derivative matrix. So dr is you take the partial with respect to the input. So the first input, the partial is 3 10t and 3t squared. So that's step 1. Then step 2, they give us a point 3, 5, 1. But that's the point on the curve. We don't want a point on the curve. We want t, right? Because I said our equation here, we need to put in t naught. So we don't want r or our point. We want t. So let's set this equal to our point on the curve. This gives us that t should be 1. So then we can step 3, find the derivative and plug in our t equals 1. What does that give us? It gives us 3, 10, 3. Okay, so now we have all our components. We have the derivative or like the slope, and then we have a point. Using our formula here, our s equals rt naught plus s to r dt. More specifically, right now we have R of T naught plus, what is this like dRdt? Well, that's our derivative matrix at the point like 3, t equals 1 times some s, some vector s. And so that gives us 3, 5, 1 plus 3, 10, 3 times s. Oh, yeah, sorry. Mhm.
You set the 3, 5, 1 matrix.
Oh, that's a typo in my notes. You should set it equal to, wait. Yeah, you should set the original curve equal to your point to get t. Yeah, because t equals 1, if you plug in, that gives you 10 actually. So yeah, that's typo in my notes. Okay. Yeah.
If there were different numbers and
Like you have like a bunch of different numbers equals this number, and a bunch of things equals this number. You can use well, then you need like different variables, I guess, like 3y plus whatever equals a number. Then you can use row reduction, that's substitution. Because now that's just like some big matrix times however many variables you have here, like x, y, equals whatever number you get. So since we only have t here, like there's no other way to make it more complicated, I guess. Unless they did like 3t plus 1 equals 3, or they could say like 3t plus, I don't know, t squared, etc. Then if you don't want to do the whole like row reduction, you could also like elimination or substitution might also work in that case. Okay, so you have this equation. This is your parametric equation, or you can write it as f of s equals 3 plus 3s, 5s equals 5 plus 10s. 3 of s equals 1 plus 3s. So you can write it in like vector form, or you can separate it into these three. Any questions on that? Okay, then let me do a statless for a 2D example. So you're finding a parametric equation for the tangent line. For the second question, you're finding the parametric equation for a tangent plane. So you do the same thing. So let me do it on my iPad. First step, we need to, okay, I found the point first. But first step, you can find the derivative, right? Step 1, you found the derivative, plug it in to our, with our t value, and we get this derivative. Then we have, then you have everything. So you have your point, you find the derivative, and you do the same thing. Follow this equation. Just now they're bigger matrices. They're 3 by 1 vectors. And so you can do the same thing, but now the only difference is that our derivative here is a 3 by 2 matrix. So you have 2 columns. So each column is going to represent one of the variables. So you put like S1 times the first column plus S2 times the second column. Any questions on, yes?
Where does the second input come from?
Second input, because our derivative matrix has 2 columns. So we need 2 variables. Here, our derivative matrix was just 1 column. So we just had 1 variable S. Okay, and you could think of this S as like your inputs. If your matrix has 2 inputs, right? It's a 3 by 2 matrix, then you're gonna need an S1 and an S2 here as 2 inputs. Any questions on that? Okay, because time is up, I'll let you guys leave, but I have one more example for today. For Taylor series. So if you were asked to compute the Taylor series for this function at the origin, okay, this question was specifically on my Friday quiz question, and I got it wrong. So I will forever remember this question. So you recall that sine v, the Taylor series, is this function here. cosine is this. 1 over 1 minus z is this function. So we have the sine z in orange, that's fine. We have the cosine in green. What is the blue? Well, the blue, you have to be careful because the Taylor series for the purple thing is 1 minus something. So if we have 1 minus x minus y, we need to rewrite that as 1 minus something. Specifically, it's 1 minus x plus y because you would distribute, you get 1 minus x minus y. So using this parentheses in blue, we use that as z. And so we follow what the formula says, we get everything. But this question says, give all terms of degree 4 or less. Degree 4 or less, meaning that if you have something like x, y cubed, there's a degree 3, a degree 1, that's degree 4, that's fine. But if you have x like 7, x 4, y 2, that's degree 5. So any terms like this, we would want to exclude those. We don't need those. Yeah. Okay, so then if you have this Taylor series, right, we have the orange times the blue times the green times the blue, not divide by the blue because the blue already has 1 over whatever. So then you can multiply these out. You notice that each time I'm like multiplying, we have xy times this term. This has degree 6. We don't need that. And times all this blue thing. And you can keep simplifying. Okay, any questions on that? Okay, free to go. Thank you.